Hello everybody. Today we are going to discuss about the experiment which is called as magnetic field due to a current carrying coil, and this method is called as Stewart method. We will take a circular coil and we will calculate the magnetic field along that coil, current carrying coil. Okay. The aim of the experiment is to study the variation of magnetic field along the axis of a circular current carrying coil. Apparatus you require is Stewart apparatus, Stewart type of tangent galvanometer, and a battery and plug key and rheostat, ammeter, commutator and connecting wires. I will show you each of these instruments while explaining the experiment and when we take the readings. For now you need not worry about what they look like. And the theory of the experiment, we have magnetic field due to the current carrying coil, which is given by B is equal to mu naught N I A square by 2 x square plus A square whole power 3 by 2. You need not worry how you got this expression, because all this is already studied in your intermediate syllabus when you derive the equation. So, you need not worry about the derivation of this experiment. Directly you will take it from the electromagnetism, and the units of this are Tesla or Weber per meter square, and where N is the number of turns in the coil. In the coil you can either select 5 turns or 50 turns or 500 turns, and in this experiment we will take 50 turns, and I is a current that you pass through the coil, and A is the radius of the coil, which is measured by a thread by measuring circumference of that coil. Circumference is 2 pi r is equal to that much value, r is equal to that value what you get divided by 2 pi will give you the radius of the coil, and x is the distance of the magnetic compass from the center of the coil. You will move the compass along the axis of the coil, and each time you note down the distance and you will note down that distance in the tabular column. And there are two magnetic fields in this experiment actually. When you pass current, suppose you have a coil, suppose this is a coil which is carrying current, say you are sending current in this direction and it is going through like this and it is coming out from this end. It produces a magnetic field at the center, all of you know this. We are going to measure that magnetic field only along the axis of this coil, but there is a magnetic field already present in this coil even if you do not send current, that is Earth's magnetic field. So, if we take Earth's magnetic field as BH and this coil's current's magnetic field as B, we will set the apparatus so that one magnetic field is perpendicular to the other magnetic field, and we will keep a magnetic needle at this place, and that tiny magnetic needle will show the resultant of both the fields. It will be under the influence of B also, it will be under the influence of BH also, and it will settle at a place which is the resultant of both the fields, and we measure that angle in our experiment, and we calculate the magnetic field by using the formula which is equal to B is equal to BE tan theta. This is another formula. This is one formula which you are using. This is another formula which you are using for magnetic field, and we compare these two magnetic fields in our experiment. This one you measure by measuring the angle, and this one you measure by measuring the distance along the axis of the coil and the radius of the coil. Okay. And the BE value which is equal to horizontal component of Earth's magnetic field, which is given by 0.38 into 10 power minus 4 Tesla. Let us see the circuit diagram of this experiment. So, this is a circuit diagram which is given in your manual. This is a current carrying coil, and this is a scale which is along the circular current carrying coil, along which you can measure the deflection magnetometer. You are measuring the magnetic field along this scale only by moving this deflection magnetometer, and this is a deflection magnetometer. This deflection magnetometer you might have done in intermediate. You have an experiment where you have this deflection magnetometer with you have the scale like 0 and 10, 20, 30 etc. up to 90, then again 0 here, 90 here. This is not from 0 to 360, the scale is marked as 0 to 90, 0 to 90, and in the middle you have a small magnetic compass with a red dot on that. This red dot indicates the north pole. This will always be pointing towards the north pole. That means however you rotate this, the needle will always show the north direction, and to this you have a scale attached. This is aluminum pointer. There is a pointer attached to that. This is aluminum pointer, and this needle and this magnetic needle and this aluminum pointer, they are always at 90 degrees to each other. They will never change the angle throughout the experiment. And here you have the two terminals to which you will give the connection. Actually there are 4 terminals. If you connect between these two terminals, it will be written 5 here, it will be written 50 here, it will be written 500 here. If you connect between this terminal and this terminal, that means you are selecting 5 turns, magnetic field is small. If you connect between this one and this one, that means you are selecting 50 turns, magnetic field is a little higher. And if you connect between these two terminals, that means magnetic field is maximum. In our experiment, we are taking 50 turns. And this is connected to the 2 terminals of the commutator. Here, the instrument which appears like 4 dots is commutator. This is called as commutator. We connect the two terminals of the commutator to the 2 terminals of the deflection magnetometer here. The other 2 terminals will go to the battery. This terminal will go to the rheostat, and rheostat's other end will go to battery eliminator. The other end of the battery eliminator will go to the ammeter, and the end of the ammeter will go to plug key, and plug key's end will go to the commutator. The rheostat is used to increase or decrease the current in the circuit, and battery is used to supply current to the circuit, and ammeter is used to measure the current, and plug key is used to make or break the circuit. This commutator is used to reverse the direction of current. If you connect these 2 terminals, current flows in one direction in this coil, and if you reverse the connection, the current reverses its direction. To begin with, we allow the current to, we will put the key here and say we have connected these 2 terminals. Now, this needle is under the influence of 2 fields. One field is due to Earth's field, another field is due to the magnetic field which is at the center of this coil. So, it will show a resultant direction of both the fields. Say suppose this is B, this is BE, it will show a resultant direction. It will show an angle. That angle is taken as, one angle you will measure it as theta 1, the other angle is measured as theta 2. You will note down these 2 angles here, theta 1, theta 2. Next what you do is, you will reverse the direction of current by connecting these 2 terminals. Then the direction of this deflection magnetometer also reverses. You get another 2 angles here. One side is theta 1, another side is, one side is theta 3, the other side is theta 4. Measure these 2 angles and note down the values here, theta 3 and theta 4, and take the average of these 4. That means add all the 4 divided by 4, that will give you theta east. And since you are not you are not moving to any side, so same values you can put here because it is at the center, so same values can be written here. And theta is equal to average of this and this, that we will calculate here. Tan of that value will put here. After that what you do is, you will move the, to start with deflection, this deflection magnetometer will be at the center when you take x is equal to 0. Now increase the distance of this magnetometer to one side. Increase the distance, say towards the east, towards this side. Okay, so measure this distance to be equal to 3 centimeters. There is a marking here, there is a marking, on this also there is a marking. So this distance you will take it equal to 3 centimeters, and you know that the magnetic field will become less as you go away and away from the center of the current carrying coil. So, definitely you will get an angle less than the previous one. So, the angle this time also you will measure some angle, that is theta 1 and theta 2, which is less than our previous case. That value you will note down here. Now, reverse the direction of the current, the deflection also reverses. This is theta 3, theta 4, which is noted down here, and take the average of this value and write the value here. Similarly, you will repeat the experiment on the west side. You will take the deflection magnetometer at some distances in steps of 3 centimeters, 6 centimeters, 9 centimeters, 12 centimeters, like that. You keep on changing the distances, and each time you note down the current. And after noting down these average deflections, you will take the tan theta of it. Hello everyone. Today we will discuss about the experiment of Stewart-Gauge experiment, which will study the magnetic field along a current carrying coil. This is a coil along which we pass a current, and inside this there is a wire, there are windings of a wire, and as you pass current through this, it produces a magnetic field at the center of the coil, and at the center you can see a tiny magnet here, a tiny magnet which is shown in black color, and this is aluminum pointer. And this magnetic needle responds to the magnetic field which is produced by this coil, by the current which is moving in this coil. So, this gets deflected, and the magnetic field changes along this axis of the coil. This is the axis of the coil, this is the axis of the coil, and we study the magnetic field along the axis of the coil. That is our experiment. Now, let us see the circuit of this experiment, and let us identify the circuit parts with the actual experimental setup. In this is a battery, DC battery E, which is shown here. This is a DC battery. In this you have one on switch here, and this red one is a positive, black one is a negative, and we see the range of voltages that you can apply: 4, 2, 4, 6, 8, 10, 12. These are the ranges which we can use by the help of this battery eliminator, and in this experiment we use the voltage somewhere in between 4 to 6. And A is written here. This is a ammeter. This is a ammeter which we are using in this experiment, and you can see the symbol A here, capital A, and below A you can see a straight line. That means it measures DC. The current that we are using in this experiment is DC. Otherwise, if you find a S shape just below A, that means that instrument measures AC. This is how you can distinguish between AC meter and DC meter. So, here we are using a DC meter, DC ammeter, which has a range from 0 to 3 amperes. And here you can see the symbol K, that is a plug key. This is the instrument which you are using in the place of K. This is called as plug key. In this you have a small brass key which can be opened. If you open this, the circuit is broken, current stops. And if you insert this key, circuit starts flowing. Current starts flowing in the circuit. And here you can see 4 dots, which is called as commutator. This instrument is called as commutator, and that instrument looks like this. This is called as commutator. In this you have 4 terminals. There are 4 dots, no? Corresponding to those 4 dots you have 4 terminals, and 2 plug keys are there. This instrument is used to reverse the direction of the current. Whenever you want to send current in the coil in clockwise direction, you insert the keys like this in opposite directions. And whenever you want to reverse the direction of the current, simply you will remove these 2 and insert it here so that the direction of the current gets reversed. Now you can see the symbol R here. This is called as rheostat. This instrument looks like this. The instrument looks like this. This is called as rheostat. On this you can see a fine wire which is wound on a cylinder like thing. This is a cylinder, and you have a sliding contact here. This is a sliding contact. You can see the sliding contact here, and you can see 3 terminals here. One terminal is here, one terminal is here, one terminal is here. And you will make contact between one terminal, this terminal and this terminal for our experiment. Whenever you make contact, that means suppose this sliding contact is here. That means we are including only this much portion of the wire in our circuit. That means current will be high. Current will be high. The resistance is small, so current will be high. Suppose I move it this side. I move the sliding contact this side. That means I am including this much nichrome wire. This is nichrome wire which is of high resistance. I am including this much nichrome wire in the circuit. As resistance increases, current also decreases in our experiment. That is how we control the current, by using resistance, by using rheostat here. And in this you can see a circle here, bigger circle and one smaller circle. The bigger circle is nothing but the coil that you are using to pass current. This is the coil which you are using to pass current. There are windings on this, and you can adjust the number of windings. Here you have 4 terminals. In between these 2 terminals, a number 5 is written. In between these 2 terminals, 50 is written. In between these 2 terminals, 500 is written. This is a ground terminal, and whenever I want to include 5 terminals in the circuit, 5 turns in the circuit, I connect between these 2 terminals. Whenever I want to include 50 turns, I will connect between these 2 terminals. Whenever I want to include 500 turns, I will connect between this terminal and this terminal. Smaller turns means smaller magnetic field, and as the turns increase, number of turns increase, the magnetic field also increase. So according to our convenience, we can choose the turns we want. In this experiment, we are going to use only 50 turns. We are not going to change it throughout the experiment. And in this, you can see one smaller circle, and you can see a black line here, and you can see one more thin black line with pointed arrows. That is this one, which is called as magnetic compass. This is a magnetic compass, and in that this is a central magnetic needle, this is a magnetic needle, thicker one, and this thin line that you see is aluminum pointer, this is aluminum pointer. And you can see the red dot on this. This red dot is a north side, this shows the north pole. This needle is as if it is freely suspended needle. That means this always shows north-south directions only. However you rotate the instrument, this will always show you north-south direction. Now coming to the experiment. There are some initial settings that you have to make with this instrument first. And look at this one. Look at this scale. This scale, you can observe a circular scale in the deflection magnetometer. This circular scale will not show you 0 to 360 degrees. Actually, it is marked with 0 to 90, 0 to 90. You can see 0, 0, 90, 90 on this scale. And below that you can observe a mirror. That mirror is arranged to remove the parallax error. Okay. If you take the readings from one side, you will get one type of reading. If you see from the other direction, slant way, you will get some other reading. No, to avoid that, always you have to look at it from the top, so that you can avoid parallax error. The initial settings that you have to make for this instrument is, you have to align this magnetic needle along the frame of this circle. Okay. For that, what we do, there are two arms of this instrument, and you rotate these arms so that the needle is aligned in the plane of this circle. And now you rotate this instrument, deflection magnetometer, rotate this so that it shows you, this aluminum pointer shows 0, 0. Aluminum pointer should be on 0, 0 exactly. Once this setting is made, throughout the experiment you will not change this setup. It will remain in this setup always. Now I switched on this battery and kept the voltage to be 6 volts here, and you can see a tiny deflection in this ammeter, and this key is inserted so that you will pass the current, and you adjust this so that, looking at the deflection in the magnetometer, in the deflection magnetometer, you will adjust this rheostat so that you get 60 deflection in that aluminum pointer.
Shows 30, 50.
You will get a deflection of 60, 60. One side of the aluminum pointer is showing 60, other side also showing almost 60 degrees deflection. Once you set this rheostat for this reading, throughout the experiment you will keep it like that. There is no need to move the rheostat or no need to change the current. Once you set the reading for 60 degrees, note down the current value here. This is showing 0.25 amperes. The divisions are 0.5 here, 0.5 divisions are divided into 10 divisions. Accordingly, you calculate how much is half of that. This needle is showing half of that. That means the reading is 0.25 amperes. Note down the current. I have taken 50 turns here. When I put it in these two terminals, when I put these two keys in these two terminals, that means I am sending current in clockwise direction in the deflection magnetometer. Now, the current is going like in this way in the deflection magnetometer, and this magnetic needle was actually showing the Earth's magnetic field before I pass the current. Now, this is under the influence of two magnetic fields. One is Earth's magnetic field, one is current's magnetic field. So, it will show the resultant direction. This is showing the resultant direction, and I note down these readings of theta 1. I call one deflection to be theta 1, the other deflection to be theta 2, and I will note down this value in the table. And actually, there is one more thing that you have to observe. There is a scale which is written on this bar. There is a metal bar here, there is a scale. This is just like your ordinary scale, and on this metal frame you can see a line. You can see a line, and initially you have to set it so that that line will be on 0 of this scale. 0, 1, 2, 3, 4, 5, 6, it goes this side, and 0, 1, 2, 3, 4, 5, 6, like that it goes to the other side. This extends towards the east side and towards the west side. In this table, you will note down the distance from the center of the coil, x centimeters. And when I started the experiment, I did not keep the magnetic needle at any distance. I kept it at the center of the coil. So, the distance is 0. And the deflections on the east, theta 1 and theta 2. One side was showing 60 degrees, the other side was showing 60 degrees. So, I will take it to be 60, 60 here. Now, I will reverse the direction of the current. For reversing the direction of the current, I will just remove these two keys and I will insert it in the opposite side. When I do it, the direction of the magnetic field gets reversed, so the deflection also gets reversed. Now also I am getting almost the same deflection, which is 61 degrees. I can see 61 degrees there and 61 degrees there. I am entering those values here. See, theta 1 and theta 2 on one side of the deflection. When I reverse the current, I am getting the deflection to be 61 degrees and 61 degrees. I noted those values here, and I take the average of these values, that is theta east. So, I take the average to be, I have to put the value here, and I can write the same values here, because I am not moving towards the east or not moving towards the west. It is the center, it is neither east nor west. So, same readings I am going to write down here, and I take the average of these two values and I can write those values here. Now, this is the average value of theta east, this is the average value of theta west. I take the average of these two values and I can introduce here, I can note down here. Similarly, Next what I will do, I will move this magnetometer to a distance of 3 centimeters, and obviously the magnetic field will be lesser than the magnetic field which was at 0 centimeters. So, obviously the deflection reduces. Now, you can see that I moved it to 3 centimeters, is 1, 2, 3. This line is showing 3 centimeters distance, and the readings would have reduced. Observe the readings here. It is less than 60 degrees. It is showing 57 degrees on the east side and 57 degrees on the west side. I am noting down those values here. And now what I do, I will reverse the direction of the current. And wait until the needle is stable. Now I am seeing the angle almost the same, 58 degrees. I am noting down that value over here. Similarly, I take down the reading for 6 centimeters, 9 centimeters and 12 centimeters by moving it towards east. After I complete this, I will move the magnetometer towards west side and repeat the same procedure. You will calculate the value of magnetic field by this formula, and you will calculate magnetic field by another formula, and you will compare these two values. For each distance, say you are taking 0 distance and 3 centimeters, 6 centimeters, 9 centimeters. So, each time you measure the magnetic field by this formula as well as this formula. Now, compare these two values. If you are getting correct, if these two are coinciding, then that means your experiment is correct. And after doing this, you will draw a graph between distance and tan theta. One set of values you will take along east direction, another set of values you will take along west direction, and you will get a Gaussian distribution curve like this, because you know that at the center the magnetic field is maximum, so deflection is maximum, tan theta value is maximum. As you go away from the center, the magnetic field reduces, so angle also reduces. So, if you get Gaussian distribution curve, that means your experiment is correct.